Hello, everyone. My name is Ali Cehreli. You all know me from the D forums and from that online book that I wrote. And let me be the first after Walter to say that I'm extremely happy to be among the DConf 2013 participants. This is really great things. Thank you very much for all the sponsors, everybody, and I know most of you are in here. It's an amazing thing to be here. So Walter mentioned how high-tech this conference is, and he's right, but this talk is not one of them. The reason is I'm going to talk about very basic concepts, like the user-defined types in D, some fundamental operations that involve those user-defined types, immutability itself, mainly the keywords const and immutable. And this talk will be more like a search of idioms and guidelines in the D programming language. So reading a book and learning about all the features is really not sufficient. As a programmer, I want someone tell me, do this, and it'll work in most cases. And just to drop a few names there, Scott Myers, Andrei Alexandrescu, Herb Sutter, we know their work for the C++ programming language. If you read their books, you know you couldn't have come up with those in 20 years yourself. So I need guidelines myself to program in D. This is just the beginning. You guys will not agree with some of what I will have, and it'll be like 4 or 5 guidelines in this talk. And I'm hoping that this will be a start for you to come up with the guidelines. And so just to see what I'm talking about. Here's an idiom from another language, C++. I use C++ in my day-to-day job, so that's why I will mention C++ a few times here. There are 2 C++ guidelines up there. Make everything const until you can't, until it hurts. Everything const is a good thing. You want to know that something is not mutated by a function or by a context. Of course, if you really want to mutate it, now you have to remove that const. Good. Pass objects by reference if they are expensive to copy. Everything, there's some guideline that we use every day. A function should take const reference if that's receiving a non-fundamental type. And there's a C++ code up there. It averages 2 values, takes them by const myInt reference, they are myInts. And the nice thing is, if you take by const reference, you can pass even a temporary, an rvalue to that function, and it works. If you make it a const locally and you take it to a const-taking function, it works too. They are not applicable in D. First of all, the first attempt here, it's one-to-one translation of that C++ to D. Here you have a const result. That rvalue will not compile, because in D you cannot bind rvalues to references, even if they are const references. And interestingly, now I'm cheating here a little bit. Instead of a const taking, I'm using an immutable taking function and passing my const to that one. That may fail in the future. If the library that implements myInt makes a well-encapsulated private modification to it without my knowing it, my code here may fail. And likewise, this line here may fail in the future for the same reason. So that's why we need better things. Coming from C++, applying those is a hurdle on the road. It's a friction. Before going any further, allow me to go over these definitions. We have 2 different type semantics in the value semantics, reference semantics. And of course, they translate to value type and reference type. We have kinds of values. A value may be an Lvalue or an rvalue. And the definitions in parentheses are usually not entirely accurate. And we have type qualifiers. Mutable, which is not a keyword, actually. Everything is by default mutable. We have immutable, const. There's also shared, which I will leave out of this talk, mostly because I'm not confident with it anyway. So just to go over what a value semantics and reference semantics are, how they differ, it's very simple to look at the behavior of the assignment operator. If you assign A equals B, after that, if you mutate A, if they are not the same anymore, if they are A and B represent separate values, separate state, like in these blue, the blue represents state there, then we have value semantics. Reference semantics is, if you look at the same code, but even though you mutate the state through one of those variables, you end up both of them seeing the same state, like in this figure over there, then we talk about reference semantics. So these are the two day-to-day concepts on semantics that we're faced in D. And then there's Lvalues and rvalues. Kind of simple to describe because Lvalues are capable. They can be on both sides of an assignment. Their addresses can be taken, and they can be bound to a reference. And there's a layman's explanation. If you have a variable that has a name, that's an Lvalue. To contrast it, rvalues cannot do any of those. It cannot be on the left-hand side of the assignment operation. You cannot take their addresses, and you cannot bind them to a reference. And this code here is demonstrating foo is a function that returns an rvalue. The rvalue can't be on the left-hand side. The address cannot be taken and cannot be passed to a function taking a ref, even if it's a const ref. And I have another slide here just to underline it. This is not possible today. In May 2013, D does not have this. But C, DIPS, and the forums, there are frequent requests for this improvement. People want that D should have const references, or rvalues should be bound to const references, because they miss this from other languages like C++, and there are good reasons for it. But today, it's not there. Now the type qualifiers. Mutable means, obviously, you can mutate that object, that state freely. There's no keyword for it. Immutable means the object never mutates. And this concept is not in C++. C++ only has const and tries to do both immutability and not mutating through a reference with the same keyword. So there's this wildcard in out, which happens to be a placeholder for the other three. It is like a template, but it's not actually, it doesn't end up producing multiple code. It doesn't generate code bloat. I will get to that in another slide. There's an example of it. But something is very significant here, as Walter said, turtles all the way down. If you have immutable state, or if you have const state, everything that can be accessed through this state, even if a member's member, they are all the way immutable down, or they are all the way const down. If you have an immutable state handle, you're guaranteed, you can be sure that that state will not change. Of course, we can find ways to do the opposite. We can change it, but that's how it is. Now, here's a chart how various languages take user-defined types. Obviously, C did not have classes, and all of the structs are value types in C. If you pass by value to a function, they get copied. C++ introduced classes to the language, and C++ made struct and class exactly the same thing, except a few access specifiers. The default access is public in one and private on the other one. Java went completely the other direction, chopped off the structs, and classes became all reference types. C# and D see it differently, and there is a value in a value type. Oh, that was a pun. And there's some value in reference types. So simple. In D, structs are value types and classes are reference types. They are different, and I say these structs are somewhere between C and C++ structs because they are not as capable as C++. For example, they don't have object-oriented programming features. They don't support that. Value types, they have scoped lifetime by default, and you can do the RAI idiom using structs. They give you layout and alignment control of the members. So you can match, as Manu will talk about actually today, if you're facing a C library, you can have the exact C ABI struct on the D side. But you can represent a C struct exactly bit by bit on the D side by structs. Classes are not like that. They're reference types. Their lifetime is garbage collected, and some objects may live infinitely throughout your program. They support OOP, and there are more differences, but these are the most important ones. Now, fundamental object operations. We know this from C++, any other object-oriented programming language. You construct an object, you use it, and then it gets destructed. But D brings two more fundamental operations that happens in your day-to-day programming, and they are actually, even though not mentioned much, they are a part of these fundamental operations. And that's the moving from an R value or swapping with an R value. It is built into the language, and it happens behind the scenes when an R value is on the right-hand side. So just to go over these a little bit more in detail, an object may be constructed from scratch on a raw piece of memory. You just build its members in there. Or it may copy it from another object, conceptually representing the same state. Or it can be moved from an R value, so that's the special thing. Optionally, some objects get mutated but incrementally through its members, member variables, or directly modifying member variables, or through member functions. Or an object can be mutated as a whole by the assignment operator. Assignment itself is two operations in one. You must copy the new state from the right-hand side, and you must destroy the old state to take everything in balance, in check. And there's this other one, and it is swapping an R value with your state. This does not involve copying. And there's always also the destruction, which is not always. As I said, some objects never die in D. They have infinite lifetime. But these are the three major things. So D has support for almost all of these operations. Structs enjoy everything. Everything is automatically handled for you. Even the construct by moving from an R value, mutate as a whole by swapping with an R value, everything is great. For classes, the concept of R value doesn't exist anyway, because classes don't take place as values themselves in expressions. They take place by, they exist as handles to those values. So the class variables are handles, so there's no R value operation for them. And copying and assignment for classes are user-defined if you want those semantics differently. Otherwise, they are trivial. As here, the default class semantics are trivial. Here we're using the copy syntax. B becomes a copy of A, but what happens is they are just two handles to the same object. This is the assignment syntax. Programming languages chose this confusion, C, C++, Java, D, we all have this. If you have this type specifier there, even if it's auto, it becomes a copy. If not, it becomes an assignment. So this is simple and nothing very interesting. I have a slide that shows if a person wants to implement copying the state of a class, it has to be done by a member function like dupe, just to mimic the same name in these arrays or in slices. You can have a dupe, and you can make a new state by copying whatever copying involves there and return it from that function. So here you see your users can call .dupe on it to receive duplicates of your object. And there may be this takeover. It's not a very common operation, but it came up on the forums very recently. Somebody doesn't want to, you may want multiple handles to the same object state. You want to change that state without knowing how many handles are pointing at it. So you can say, hey, take this state, and one of them takes over the state into that existing class object. Now all three sees a new state. I don't think it's a common operation, and it doesn't go with a reference type anyway. But if you want these semantics, you have to write them on your own. That's how classes work. And as promised, this is how in-out works. if you make a member function inout and specify inout throughout its implementation, including on the return, that inout is either mutable, const, or immutable, depending on what you call it with. So I have a mutable, immutable, and const objects here. Call dupes on them. As you see, these static asserts all pass. The duplicated, the copies all carry the correct type of the original. So that's one slide that uses inout here. Okay, this is how a struct object gets copied by the D language. Two-step process. And this is one difference from C++. There is no copy construction is involved. D goes ahead and takes the bit structure, all of the bits of the source, copies on top of the destination, onto the raw memory. And obviously, this act makes self-referencing structs invalid objects in D. No object should have a pointer to itself. Otherwise, if you move it here, the pointer is still pointing to the original location. And then, as the second step, and if it's defined, it executes the postblit function. And it's to make some corrections, because you don't want two sets of bit pattern having the same value. They may be pointing to the same data as in here. You may want to duplicate all your data. You can interrupt me anytime. I've never told you so, but please let's have a conversation if there's any question. So now I think, yes, so this is the struct semantics for Lvalue appearing on the right-hand side. They have a little different meanings from the rvalues, because if you already have an A variable, and which means it's an Lvalue, this copy, this operation is semantically is a copy. And if you have an assignment syntax, and if you have an Lvalue on the right-hand side, that is semantically copy and destroy operation. B becomes a copy of C, and B's old state must be destroyed. This is how struct copy and assignment syntax work for Lvalue on the right-hand side. And the assignment part is needs some talking, actually. When you have an Lvalue on the right-hand side, and you have that assignment, what happens behind the scenes is, obviously, the source must be copied. But the D language is a little better than C++ in this regard. It makes the copy first. And only if the copy succeeds, it bit swaps it with that temporary copy. The old state is bit swapped with the temporary copy. This is for correctness. Not to bash on C++, actually, but C++'s default assignment behavior is not strongly exception safe. Say you have a struct that has the first name and last name of a person. C++ will go ahead and do a member-wise assignment of the members in order. If the first name assignment succeeds, but when you get to the last name assignment and it throws, you end up with a half-assigned object in C++. And that's why if you want to have a strongly exception-safe assignment in C++, you must write that assignment operator yourself, and you must use this idiom anyway. Copy first, and then swap. So D handles this for you automatically if you have an Lvalue on the right-hand side. So rvalue on the right-hand side is, again, pretty cool, actually. This is what C++ has brought, C++ 11 has brought with the rvalue references concept to allow you to move data. And here's a function that returns an S represents a struct here. If you're constructing a variable, so this is again the copy syntax actually, and you have an rvalue result on the right-hand side, this simply moves that state, the rvalue state, into your newly defined object. There is no copy involved here. It bitwise moves it over here. But of course, it must elide the destructor on that rvalue that is returned. So it's just a bitwise move. On the other hand, if you already have a variable a, then as you know, this becomes the assignment syntax. Now what happens here is a swap, effectively. The r value on the right-hand side is swapped with a, and a's old state is swapped with the r value, so that the rvalues destructor will destroy the old state. These are fundamental, built into the language. I should make a comment here. I used to have a slide here. It is out of context in a D conference, of course. C++ and other languages use RVO and NRVO optimizations, return value optimization and named return value optimization. Those optimizations cannot be done in every situation. There are cases your function may have 2 return statements in it, for example. They may not be applicable. But this method, move and swap, is applicable in any case because it's a bit move and bit swap. Walter, correct me please if I'm making mistakes here. It is awesome to have all these amazing people here, all these experts in here. I can say anything I want. I know somebody will correct me, hopefully. So again, looking more into what happens when you have an r value on the right-hand side in the assignment, it's actually effectively a bit swap. And when we leave this context, the rvalues destructor will destroy the old state of dest. Simple. Okay, now I want to talk about how to use immutable and const for a local variable versus in a function.
Well,
Yo.
I guess this is going without saying, but when you're talking about a swap happening, this is just conceptual and it's optimized away, right? I mean, but does the compiler actually do the swap at some, say that it's swapping it and then later just leave it up to the optimization to optimize that swap out, or is it just purely conceptual and the compiler never actually does a real swap?
I know David Nodlinger knows the answer for that.
The swap happens.
Okay.
That doesn't mean it couldn't be optimized out. There's a lot of optimization potential that isn't realized yet in the current
Yes.
decompilers. I mean, there's a lot more that can be done, but currently the swap does happen.
Okay. But at least it's a cheap bit level swap, right? There's nothing else there.
It's a mem copy style
Yes.
swap.
Any questions for Walter? No. Okay. So, immutable and const. As a person who came to D, and I'm sure many of you are, or obviously, and there will be most people do this, go through this. So we know how to use const in C++, but we have this immutable as well, how to make use of this. So let's play with this a little bit. If I have some state that I know it should never change, I can mark it as immutable. There's an integer, and there's a struct variable, and mark them immutable. There's this deep guarantee, as I mentioned, turtles all the way down, everything should be immutable through those variables. And there are 2 bonuses here. One of them I forgot on this slide. One is immutable is implicitly shared. Because it never changes, you don't need to lock that in multi-threaded code, for example. It's read-only. And the second bonus is, I've heard it many times in the past couple of days, that immutability gives the compiler opportunities for optimizations. That's right? I mean, the compiler can take advantage of this too. So there are 2 bonuses of it. And of course, it must be a little useful. If I have a mutable variable here, I should be able to create an immutable copy from it. It works. Awesome, because it's just, but there's no problem with it because it's a copy. Likewise, if I have a const, I can make an immutable from it. And I say this slide is too optimistic because we'll see that there will be issues with this later on in coming slides. And then there's const values. Just look at the 2 slides. They are very similar, actually. I'm just replacing immutable with const. And the same thing happens. There's this deep guarantee, turtles all the way down, everything is const. And const doesn't have any compatibility with shared because it doesn't guarantee immutability. It just says you cannot change the state through this reference, but const doesn't know whether the original state is immutable or not. And likewise, you can create constant objects from mutable or immutable, very convenient. So let's try using these two in a program. And this program has 3 functions. One takes by value, the others take by immutable ref and const ref. So if you go with the immutable path, you notice that all 3 functions can be called with that variable. But if you define a const, the one that takes by immutable ref cannot be called anymore. So const looks like a less useful type qualifier for a local variable. Okay, then I'll go with immutable. So here's my guideline. And I say this is deceptive at this point because there will be other issues later. But here's the guideline. If a variable is never mutated, make it immutable, not const, because it'll be more useful in the future for you. Now, I'm moving towards a const reference. What is a const reference? And there's a reference type. As I said, the classes are reference types. Const is inclusive. A const reference can refer to mutable, immutable, and const. And I have 3 examples here referring to mutable, immutable, and const. And there's an important footnote here. Const actually erases the qualifier of the original object. If you start having a const reference, well, these asserts pass again, the type of C is const C. You have no idea what the original was anymore. So that's okay, that is still very useful. These slides have not been changed. There was another version of it, but that's okay. Okay, so there's nothing different on the next slide. This was const references and they are all local. Let's put a const reference on a function parameter. And this is again great. This function can take mutable, immutable, and const. Here, I can pass all of them there. So when you have a function like this, the semantics, the message that the function is giving out is, I shall not mutate your argument, which means you can give me anything you want. I'm not going to touch it. This is great. So, but that's the message that a const reference gives out. And again, I'm noting here that if you do this, though, the P itself has no idea what the original has been. The original type qualifier is lost. It's just const in there.
Ali?
Yes?
What happens if you do try to mutate an immutable through a const?
Oh, you can't. You cannot mute. Oh, so I'm sorry. So what happens if you try to mutate a const object? You mean P. Yeah. What if you try to do operations that will mutate P or any member of P? The compiler doesn't allow you.
Even though it lost it?
Yes, because a const is a guarantee that you cannot mutate P nor any state access through it. And that's the fundamental reason, actually, that you can pass an immutable to it, because the function gives you that guarantee. So immutable references are less interesting because you can have an immutable reference only to an immutable value. Right? Because if you have a mutable or const, it's not really guaranteed. Mutable is not, and const doesn't know. So only the middle line there compiles. And moving the same concept to the same function, let's now define a function that takes an immutable reference. See, I can only pass an immutable to that function. So it looks like limiting here. But the message that the function giving out is very interesting. Const function was, or the function taking const was inclusive. It says you can give me anything. But this function here says, I shall not mutate your argument, and the compiler will check for that, of course, but you must not mutate it either. So this is a demand. When you have an immutable reference, it's a demand to the outside world that I need immutable, please.
So what if you pass a const to a function and you want that function to modify it temporarily for performance reasons and use the modified copy, then change it back to what it was before the function exits, and guarantee that the function does that? Can that be done?
Well, this being a system language, you have all the tools to bypass these. At the lowest level, you can cast a const, modify it, but then you're in an undefined territory. You must know that it was not immutable. It's all in your hands at that point, but there are tools to do that. And here's the correct answer.
Yeah, I want to react.
I just wanted to expand a little bit on that. If you're in a const function and you cast away const and change it and then put it back, you've potentially corrupted your program. And the reason is because that const object could really be an immutable object. And remember how Ali said earlier that immutable means there's implicit sharing between threads.
So is there a way to enforce that you can only pass a non-immutable thing, object to a function that takes it as a const parameter?
Right.
But someone else
This is getting out of hand here. Write to overloads, and you can, like the immutable overload can do whatever it takes to conservatively handle the immutable state, and the other const overload is gonna know the object was not immutable. Wow, this is awesome. Thanks.
So again, just by looking at this one, the earlier one, if I make the parameter immutable, I'm limiting my callers. So we can say, again, some deceptive guideline is this one. If a reference parameter is not going to be mutated by the function, make it const, not immutable. This is looks like a nice guideline because now I have this pretty print function. It takes a const string, where not the string itself const, of course, indeed the elements of the string are const. You can call it with mutable, immutable, and const. It works very well. And after all, if you have made it immutable, you could only pass a string to it, and your users couldn't call your function with mutable or const. So this guideline is good so far. But now, instead of actually mutating the object, I don't want to do that. My pretty print still takes this, follows the guideline and takes by const char. Let's say in the future you want to change the implementation of pretty print, and you need to call a function that takes by immutable. And I'm sure everybody here knows that string is a string with string made of immutable characters. So string is an alias for immutable. Now you're in trouble. You made your pretty print convenient for your users, but you can't call an immutable function inside there anymore. What you have to do is go through this pretty useful function that we have in the conv module in Phobos, pass it through, you say convert str to string, and now it compiles because you actually make a copy of str. This involves a copy, because the compiler at this point is not sure whether that's immutable or mutable. It must make a copy. So what happens is you're making the function convenient for your users, but you're making your program slower if they already have an immutable. There's a solution here, because D has templates and very powerful ones. You can write this simple template here. Convert your pretty print to a template. And because this here is actually a constraint on the parameters, give me only a string, you can use a template constraint to constrain it, make it more similar to that function. Then you can always pass your parameters through to string. The good thing about a template solution is templates always retain the exact type of that is passed in. And toString is so smart that it will not make a copy if the parameter is already immutable. So you can go ahead and do this here, and it will be a no-op if it's already immutable. This is a solution for this condition, but it doesn't look very appealing. It doesn't read as cleanly as the other one. You have to go into this constraints if you need to, and you have to do this all the time. Okay. So our guideline 2 has been deceptive. Yeah, for this reason at least. It gives you a problem with your function implementation in the future. And here's another one. Let's say you make a constructor parameter, a const string. And let's say this is an archiver and needs to maintain the passed-in parameter because it's going to use it in its destructor. So this struct actually needs immutable data. The string must not be mutated throughout the lifetime of this object because it is going to be used in the destructor. If we go with the guideline and make it a const string, now the struct itself must duplicate what is given to it because const has erased the actual type of it, the type qualifier. And that, again, this copy is unnecessary if it were an immutable to begin with. So we made it convenient for our users, but it's unnecessarily expensive in this case. So let's revise this guideline. We made a mistake by saying take by const. And the revision is, of course, if you're going to actually need immutable data, it's better to make it obvious in your API so that your caller's now responsible for making a copy when needed. And in this case, when you make that string, you don't make any copy anymore. You can safely put it in there because you know it's immutable. Have your callers make the immutable duplicate of the string when necessary. This is great. But I saw this a little bit of implementation detail leaking out of a struct. We used to have this awesome encapsulation where we said, I don't care, you can give me anything, and you don't need to know what I do with it. In the earlier one, I would duplicate it myself. But it turns out, in D, it's no big deal. D necessarily brings the implementation and the caller together to give you faster programs. So in this case, it's okay to ask a favor of your caller, saying, I will use it in an immutable way anyway. Please, you give it to me. That's how it is in D. So, and here's the revised guideline. Make the parameter reference to immutable if that is how you will use it anyway. And it's fine to ask a favor from the caller. Now I go back to guideline 1. And it was, if you're going to have a local variable, make it immutable, was the guideline. So far so good. It works just fine. You can copy from a mutable one, from a mutable to immutable, it works. Let's say my int is a library struct, and that library's implementer adds a very well encapsulated private but mutable data itself. Now suddenly your line doesn't compile because immutable demands immutable data. If you have m, it's not mutable. If you copy it here, then even though I thinks it's immutable, m has a mutable reference to the same data, so it is illegal. It errors. And then I'm revising guideline 1 again. Maybe const is better after all. If you have a local variable that you're not going to modify, make it const. Because then the library can change it any way they want, and you do this. I'm not actually sure about this myself. It depends on your situation. It depends on how the library struct is implemented. But this syntax is problematic in itself. I will get to it later in my last slide, I think, or the one before the last. So this syntax is problematic. So I'm revising guideline 1 again. If a variable is never mutated, make it const. And I mean a local variable in this case. So if you make it const, so we're back to the origination of this guideline 1, what if I made it const here? What if I want to pass it to a function that wants immutable now? I know I can't pass it. This slide is just introducing assume unique. I'm sure you know all this, but assume unique is a very nice library function. There's no copying involved. It's a no-op, basically. It shreds your original const object, makes it null, and gives you an immutable handle to that same state. Nice. You can easily convert it to immutable. This is the bad slide, so this should be the other way around, and it should say avoid. Of course, avoid casting non-immutable data to immutable. Only if foo is implemented in a wrong way and you know that it requires immutable unnecessarily, maybe you can do this, but not a good idea. Or in the end, if you started with a const state and you have to make immutable, you can just make a copy at that point. Here's another controversial situation. We have a foo function that makes a result, a string in this case, and returns it. Should it return an immutable string or a mutable one? Well, if it returns immutable, it's limiting the caller unnecessarily, because the caller may just get that result and start modifying it. But of course, it won't compile this line, because S is immutable, or because of the immutable there. But if you make it mutable, now it compiles, very convenient, your caller is happy. But what if the caller wants to treat it as immutable? So that's a useful function, returns by immutable. Now this won't compile. You have some options. If the function were pure functions returning mutable data can be implicitly converted to immutable. That compiles, because the pure function guarantees that this mutable data is not referencing outside. It produced it and it's the result of it. You can do this. Or your function can be documented saying, hey, I return a unique string. You're safe to pass it through assume unique to get an immutable data out of it. That works too. These are some solutions. Sorry again?
That is true so long as they are returning values, I guess. Because I'm wondering, if they're pure functions, they can only be returning values, right?
Yes.
Okay, never mind.
But in this case, it's actually a semi-value type, right? The slice itself is a value, but it refers to data that it doesn't own.
I guess what I was wondering is a pure function can be actually run only once and cached. So basically, every time it's invoked again, the old immutable value would be returned again, but it's not shared.
Yes.
So we should be fine.
Yes, it is
correct?
fine. Yes.
Thanks.
And
Sorry.
that's why the language allows this, actually. It's a very nice feature that you can do this.
Thanks.
Thank you. So I've promised that this syntax has been problematic, at least again in May 2013. Because this one uses the immutable keyword as a type qualifier, not as a type constructor. Here, the same keyword is being used as a type constructor. There's a subtle semantic difference. If you have the first one, what you have on the right-hand side is typed as S. It's not an immutable S. You make an object of type S, and then you say, let S0 refer to that state in an immutable manner, effectively trying to make its every member immutable. But this one says, I want you to construct an immutable S. From its conception, this object should become its life as an immutable. And then I want to refer to it as S1 variable. The semantic difference is start your life as mutable, start your life as immutable. And the problem here is, if S has a mutable indirection, the first line will not compile, because there is no mutable to immutable conversion if that's a reference type over there. But this will compile. So here's another guideline of
by casting it to immutable, will it automatically copy all of the mutable references into something immutable? Or how does it? Oh.
well,
Never mind.
Yes, but if the type has an immutable constructor here, I'll get to that actually. You don't need that. This syntax is already supported for a good old constructor. It will construct an object and then make the object change the members types to immutable without passing through any assignment like that. And maybe this is a question, should these two lines have exact semantics or not?
I think you got it.
Okay, all right. Yeah. So then we should prefer the second syntax here. And just to end my talk here, if you want to write a struct, this is one way of doing it. And these are the tools that you may want to implement. And look, this struct has a mutable indirection. It has some data that it uses for its own, probably. It may have other members. Let's say it takes some completely unrelated string s parameter. This is your constructor. And you set your data to 42 something. You will need a postblit so that two separate objects are own their separate data. As you remember, postblit is executed after a bit copy. So you may have to do this data dup to have your own data. This one is not a copy constructor, again. This is a move from rvalue. If you define these two functions at the same time, because rvalues cannot be bound to a reference, rvalues will go to this function, so you can safely move that rvalues members to yourself. When you're constructing an S object, you can safely move. No need to copy, no need to worry about this, that object over there. It's your rvalue to steal all the members from. But if you hit this function, you know the semantics here is copy from Lvalue. Because rvalue would go there, Lvalue comes there. Just do your copying, don't touch that one. And you made it const to promise not to touch anyway. And then you have the op assigns. Again, if this is by value and this is by ref, swap with what is given to you so that your old state goes to that. And when he goes out scope, you destroy your old state. And this one is for copying from an Lvalue. You must make a copy of what is given to you, and you must also either destroy your old state explicitly or rely on the garbage collector, however your members are. Ben?
Most of this is just optimization, right? Like, you wouldn't always have to do this.
Yes and no. Oh, I'm sorry. Ben is asking whether most of this is for optimization or not. You wouldn't need this. Well, you would need these move and copy constructors still, for this reason. If your users, I'm sorry, this wouldn't work anyway. Do you know the answer? Let me think about this. Actually, no, you're right. If you use the recommended signature here, and let's say if it take a string, it would go there and generated it for you. But no, you need these. Because the assignment will not allow it. From a mutable to immutable, assignment will not work. If you have this mutable data on the right-hand side, and if you're trying to copy an immutable on the left-hand side, that syntax won't work. And I think this is the summary of it. As I said, these are not cast in stone guidelines, and as you've seen, there's a push and pull between all of this. I think I've had only 4 of these, and I think that's all. More questions? Hey, thank you.
Hello. I haven't been able to read your book yet, but I guess asking you as someone who has to explain all the nuances of the language, I mean, what's your take on the complexity of D? And then I'd maybe ask Walter and Andre, watching something like this, do you feel satisfied that things are really distilled down to kind of as simple as they can be for the language?
Well, interestingly, first of all, it takes time for a language to be understood. And one example from C++ is exception safety. It takes at least 4 years. It took 4 years for the community to understand how to use it correctly. So in that regard, it may take time. But for a beginner programmer, I think D is an excellent language because it has the garbage collector, and the user need not deal with most of this stuff. They just write their code and everything works easily. Slices make it easy, strings make it easy. That's my take on it. But as you see, there are concepts in the language for the outsiders must understand and must learn how to use. That is true, and that takes time. But Andre has an answer for that.
Since I've been explicitly named, it's so essentially my understanding of the question is, are you happy with what it took to get the job done? Because the job that was to be done was to make sure that in the same language we have proper handling of immutability, like true functional immutability, and imperative style of programming. And at the boundaries between the two, there's going to be inevitably some seam. There's going to be something going on. And that's a difficult proposition to address in any language. And all languages have difficulties with it. It's well understood. And indeed, there's also the constraint of doing it efficiently. Now, my answer would be like just with people, like it's easy to find a beautiful person, easy to find a smart person, easy to find a person who's early back home, easy to find a person who's a great athlete, right? It's very difficult to find all of the above embedded in the same person. What we're trying with D is to embed within the same language all of the above, like good athlete, beautiful, all that good stuff. So my answer is probably we didn't get like the absolute easiest way out of this, but I think we're at the point right now, especially with this whole pure function returning a thing, and it becomes immutable. So you kind of have a very elegant way to combine the two worlds. Well, if it's a pure function, by definition, it can't return mutable state. So wow, this is kind of some realization that you're having, like, oh my God, so purity and immutability and the lack thereof, they come together very nicely. So I believe we have a good solution, and I believe I'm happy with it, and I think it's a necessary cost in a language that needs to do so much.
And I have a question to Walter. Can we hear more about what the compiler can do with immutability inference?
Oh, that is a really great question, and it's definitely something where we keep discovering things we can do. I realized a few months ago, based on some newsgroup postings, that the compiler can actually go a long ways toward inferring that it can make otherwise mutable expressions. It can infer that it can implicitly make them immutable. And I think there's an awful long way that we can push that so that we can construct immutable objects out of mutable parts and be able to prove statically that we can convert it to immutable. And that's really the direction I want to go with this. It should greatly simplify the construction and building of immutable and shared objects. It turns out there's awful lot of expressions. A simple example would be a new expression. New returns a pointer to mutable data. But if you think about it, since it's unique, it can be implicitly cast to being immutable or shared. And so once you start and pulling on that string, you realize there's an awful lot we can do to implicitly do that. And that's the direction I want to go with that. And so that's an active area of improvement. I think we're out of time.
Yeah. But don't we have 10 more minutes? Yeah, Amawi? Oh, 2 more minutes.
Okay, I want to react to what Walter just said. When you do this kind of implicit conversion, you throw away something, which is the ability to optimize the garbage collector according to type qualifier. For instance, we know that OCaml's garbage collector is more efficient than Java's, for instance, even though there is way less resources dedicated to it, because the language is so friendly to garbage collector, because most things in OCaml are either thread local or immutable. And what is their plan to use that in D? Because right now we have all the information about that in the type system. So do we want to use that in the garbage collector, or do we want to go to the past to more implicit conversion, and through that away, basically, through that optimization capability in the garbage collector away?
I feel that's an excellent question. And I think we can have our cake and eat it too. Because if we're inferring that what's coming back from new, we can implicitly cast to immutable, there's no reason why we can't run that inference back down and rewrite the new to calling an immutable new. So, although the compiler doesn't do that right now, there's nothing in the language semantics that would prevent that kind of optimization and improve garbage collector thing. So I think definitely we are not precluding that. I think we can have it both ways.
Any more questions?
I think we're out of time.
Okay. Thank you.